way that I would look at it is, what is driving precision medicine today? In oncology, which is my specialty, I think clearly genomics is making tremendous strides. There are exquisite examples today where we're able to identify and be in a very great position on how to treat a patient simply relying on genomics. However, you got to flip your coin. There are still many instances in oncology where we do not fully understand the biology and how these individuals are responding to their treatments. That's where I see now proteomics filling a very critical piece of that information. So what we're trying to do at the NCI through our initiatives is to begin to converge these disciplines. And quite frankly, partly I think the reason has been is the evolution of technology. Genomics technology has matured and is still maturing at a faster rate. But as proteomics technologies are also maturing, and also we could go after smaller samples, it's just a matter of time that these disciplines do begin to converge. So that's where I see these two areas being very complementary to one another, specifically in the area of precision-based medicine for oncology. Proteomics, the way we know it today, would not exist without mass spectrometry. Pure and simple. Genomics gave us a blueprint. What people did within the specialty is, there was an acknowledgement, here is a mass spectrometer. Mass spectrometry has been used in clinics for over 30 years for different purposes. It's mainly used for small molecule screening. But then there was a brilliant idea that came into play. Can you take a big protein, break it apart into small pieces, into these peptides, and informatically, just like an eloquent puzzle, stitch it back up into a protein? Without mass spectrometry, proteomics as we know it today simply would not exist.
As part of the Human Protein Atlas project, we've been making a cell atlas, a subcellular map of the human proteome, using an antibody-based approach. The most interesting findings we made here is that as much as half of all proteins localized to several places in the cell, and we also see a lot of single-cell variation. As a young scientist, I would focus on the integration of different omics technologies and even assays that cross dimensions. So, for example, to integrate sequencing data with proteomics data with imaging data at both the cellular and multicellular level. I think that's a dimensional challenge that we'll have, and I think that's a very interesting one to tackle.
That proteomics is going to make an impact in the clinic multiple ways. The first way, especially in acute diseases where you're not really looking at gene changes or the genetics except as a risk predictor, I think it's really going to be the proteins and metabolites, the very fast-moving changes that are going to be the ones that we can go after. And I think we already know examples in where it's been protein-based have been the biomarkers in these acute diseases. The challenge comes often with chronic diseases where you're going to need to look across multiple omics to really refine where that individual is and how they're going to respond to therapy. When we do that, and with the proteomics that we're doing, we're going to need to look at isoforms and post-translation modifications and other dynamics that will allow you to have really the breadth of response that you need to be able to have to determine that individual's response. We're using targeted mass spectrometry or targeted multi-ELISA platforms to really push into the very large clinical utility space which is needed for adoption.
When we learn about proteins, I think we should try to study the proteins as they are. And so that's my answer to saying, okay, we should do native or top-down proteomics or middle-down proteomics or glycoproteomics. It is very clear that the conventional workflows are not optimal yet, especially in the field of sequencing for glycopeptides and for intact proteins. We don't know yet how to do that best, but we know that CID, collision-induced dissociation, is not sufficient by itself. And that's why we and others invest a lot in electron-based fragmentation techniques, but also combinations of ETD and HCD. And we have shown that this so-called ETHCD is really beneficial not only for glycopeptides, also for cross-linked peptides, for MHC peptides, but also for intact protein.
Assays are already used in clinical applications, but to measure small molecules. Now, when it comes to proteins, there are additional challenges, and the first challenge is the dynamic range of protein expression, which covers several orders of magnitude in biological fluids and also in tissues, and this somehow precludes identification of low abundance proteins, which very often are very interesting targets for biomarker as potential biomarkers. The second problem is that to implement targeted proteomics in a clinical setting, you need a sophisticated instrumentation, mass spectrometers, and you also need a highly trained personnel, so people that can run these instruments and that can also deal with instability issues, for example, of the nanochromatographic system coupled to the mass spectrometer. And the third problem is that SRM assays don't have yet the same throughput of ELISA assays. So I would say these are the limitations, but on a positive note, I think as a community we have already succeeded in demonstrating that targeted proteomics has very important features that are crucial for clinical applications, and these are low coefficient of variation, and also the interlaboratory variability is very low, so this is very important.